possible. Но не важно.
So, please, I should speak English, right?
Ну,
Yes, yes. Certainly, of course, not here, so this we don't understand Russian codes. But just in case, I would prefer to speak English because I have seen some French colleagues online. So today I will talk about a remarkable thing regarding statistical models, which on models transversal junctions in circuit conductivity. And on the other hand, it is related to many other domains of mathematics. So we can be rewritten the system of linear equations on the atmosphere. And it is happens to be related also to isomorphic information of the equations. So let me just first recall the basic stuff. One correct relation first we will define it for circles, and then we define it for rational terms. So let us consider a positive orientation preserved circle homomorphism. And let us define the rotation number as follows. First, let us take its lift to the universal coordinate given line. It is given by one of the same formula as was in several circles of the line. So f of x is equal to x plus g of x, where g is 2 periodic function. So our circle is the quotient r over 2 pi z. The rotational number of the lift is defined as this limit. This limit of the case integral of f applied to x divided by 2 pi k, and this limit happens to exist. And moreover, it is well defined as an invariant of circle map up to integer number, because definitely the lift point up to graduation 2 pi n. That is integer, and when we up to pi n lifted, then m integer number is added to this value, to the rotation number, and therefore if we reduce the rotation number modulo z, this is a well-defined invariant of circle homomorphism, and the limit happens to be independent of x. And this rotation number was introduced by people. Let us consider basic examples. So the rotation number is nothing else, but it is generalization of rotation. Namely, the rotation number of rotation of n by angle 2 pi a is equal to a. The circle homomorphism has fixed point if and only if it has zero rotation number. Similarly, it has q-periodic point if and only if its rotation number is rational number with the number with denominator q or its divisor. And now let us pass to families of circle homeomorphisms, depending on some finite dimensional parameter u. And this yields a rotation number function, which sends a parameter value to the rotation number of the corresponding circle homomorphism. And now let's introduce one of the main definitions. It is a variation of Arnold terms. Consider a level subset of the rotation number function. So the subset of all parameters for which the rotation number is given to is equal to the given value r. And if this subset has non-empty interior, then it is called phase-lock area. So phase-lock areas are those level subsets of the rotation number functions which have non-empty interiors. Let's consider basic examples where such a situation happens. Consider a family of circle diffeomorphisms. And that for some parameter value, the corresponding diffeomorphism has q-periodic point for which the q's iterate, which fixes this point, has a derivative different from 1. Then, by implicit function theorem, it follows that if we perturb the parameter, then the periodic point persists. And this implies that for a neighborhood of the given parameter value, the rotation number remains the same, and it will be equal to p over q for some integer p. And therefore, L sub p over q is a phase-lock area. And this example illustrates classical fact, stability of the periodic point under small perturbation.
Sorry, could you again repeat the definition of the phase-lock area?
Phase-lock area, it is consider a level subset of rotation number function. Consider give a fix in R and consider those parameter values for which the rotation number is equal to R.
Correctly. I have natural number.
Not necessarily.
Not
Not necessarily. It can be rational number. Any real number, by the way. Because if you can consider trivial example where all the maps are the same for all u. In this case, and you can consider such an example with irrational rotation number. And this gives an example there of phase-lock area with irrational rotation number. But it is a very degenerate example. So it's okay?
Yes.
I'm sorry about how I'm sorry.
А скиллсы мне легче ставить?
That's the point. Okay. Is the size or is such a size is okay for everybody? Okay, thank you. I think that's okay. 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 Thank you. But now I would like to have the entire slide. Okay. A little big. I would like to bigger.
Тут лучше уже закрыть и открыть заново.
Очень закрыть заново, потому что тут несколько файлов, несколько слайдов одновременно возникают. Давайте. Закроем заново. Ага. Okay, let's try like this. Thank you. Let me recall some other basic stuff about Arnold family of circle diffeomorphisms and Arnold tongues. So Arnold considered the following two-dimensional family of circle diffeomorphisms. X is sent to x plus 2 pi a plus epsilon sine x. So there are two parameters, a and epsilon. So for epsilon between 0 and 1, strictly less than 1, this map is a circle diffeomorphism. And the phase-lock area in this family are called Arnold tongues. They are presented here. They are marked by yellow. And it happens that for every rational number, the corresponding level subset of the rotation number function is a phase-lock area. So for each rational, so if epsilon is equal to 0, we have pure rotation. And if you take any number p over q on the horizontal line, then it yields a non-trivial phase-lock area up, which enters the horizontal axis at this point. And if we take a cross-section, horizontal cross-section of this picture, and you take the complement to the phase-lock area, you obtain a contour set of positive Lebesgue measure. And when the height of the horizontal line goes to 0, then the complement, then the measure of the Arnold tongues tends to 0, and the measure of the contour set tends to the full measure. Now let us consider flows on torus, and let us define the corresponding rotation number. We will deal with torus, which is quotient of R2 over 2 pi integer lattice, and we will deal with flows on torus which are monotonous in one coordinate. So up to rescaling by some function, the flow takes this form, where f is 2 pi periodic in 2 coordinates. And each solution is, of course, uniquely defined by its initial condition. And the rotation number of a solution is defined like this. You lift solution to the universal covering line. This yields a real valued function phi of t, the value of solution. And you divide it by t. And as t, the time tends to infinity, the limit exists, and it is called rotation number. And of course, a priori, it depends on the choice of initial condition, but in fact, it does not depend on the initial condition. And it is related to the previously defined rotation number for the circle as follows. Consider the Poincare map of the flow. This means 2 pi time flow map. Take a transversal cross section. Take just the coordinate circle with coordinate phi, and tau equals to 0. And this cross section is mapped to itself when we apply 2 pi time flow map. And this map is called the Poincare map. Initial condition is sent to the final point with first arrival of the trajectory to the same circle. And the rotation number is independent on the initial condition. And if you take it modulo z, this yields the rotation number of the Poincare map, the invariant of circle map, which is modulo z. So the phase-log areas of families of flows is defined as before. Consider a family of flows on torus which depend on finite dimensional parameter, and consider a level subset of the rotation number function. And this level subset is called phase-log area if it has non-empty integer. As in the previous example, let us consider the situation when for some parameter value, the flow has an attracting or repelling periodic orbit. This is equivalent to the condition that the Poincare map has either attracting or repelling a periodic point for some q in integer q. Then the period of orbit is equal to 2 pi q with integer q. And the rotation number is equal to p over q for some integer p. And this can be easily seen when we calculate the rotation number along the chosen periodic orbit. And when we perturb the parameter, for the same reason as before, the by attractivity or repulsivity, the periodic orbit persists under the deformation, and the rotation number remains the same, but because its way of calculating along the periodic orbit does not change, and when we move a periodic orbit continuously. And therefore, we have a phase-log area corresponding to this rotation number. And our goal is to study phase-log areas in a spatial family of dynamical systems on torus, which models the Josephson junction in superconductivity. First of all, let me recall the physical context. So superconductivity is a phenomenon when the electric resistance becomes exactly 0, and it occurs in some metals as temperature becomes very small, smaller than some critical value. And the resistance happens to limit some positive value when the temperature tends down to the critical value, and then it jumps to 0 when T crosses the critical value. And supercurrent is in zero resistance is carried by coherent Cooper pairs of electrons. And Josephson effect was theoretically predicted by Brian Josephson, who was at this time a master or a PhD student in 1962. And it is the following phenomena. Consider the system of two superconductors separated by very narrow dielectric or a very narrow metal layer. Thickness is very small, much less than distance of electrons in Cooper pairs. pair, and and he predicted that there should exist a supercurrent through the dielectric which crosses the junction, which goes from one superconductor to the other. And for later on, this prediction was confirmed experimentally, and Josephson shared Nobel Prize in Physics with two other physicists for this discovery in 1973. And Josephson effect is described by quantum mechanics. The state of each superconductor is a complex valued wave function of time. Let he, J, denote its argument, and let phi denote the phase difference, the difference of the arguments of wave functions of superconductors. Arguments are called.
Okay, could I ask a question? Yes. If I understand right, the physical problem there are three parameters: frequency, permeability of conductor, right, and distance between superconductors. Okay, so three physical parameters. Okay, could you explain how they appear in your coefficients? We have some equation how these coefficients are related to real physical parameters, which are frequency, permeability, and distance between.
So the relation is the sense of these parameters is the following. You write down the Kirchhoff law saying that the algebraic sum of different components of the current should be zero. So here, what is written is nothing else but different components of current. This is so. First of all, let me just explain some Josephson relations. So Josephson also predicted some equations governing the Josephson junction. That the supercurrent crossing the junction is equal to some constant times the sign of phase difference. And Josephson, this is first Josephson relation, and the Josephson voltage relation states that the derivative.
Still, the question about the second derivative. Please explain.
Yes, I will explain. But first of all, I would like to.
Okay, to set up the previous.
I would like to make a setup. Then I will explain. Okay. So the voltage relation states that the voltage on the junction is equal up to known constant to the derivative in time of the phase difference. So this means that the quantum mechanics value phi has macroscopic meaning. Its derivative in time is equal to voltage up to known constant. And now let us pass to this equation to the general mathematical model of Josephson junction.
Before you go, could I ask a little bit more about physics? It's clear from the school physics that the distance for the GA junction should be much smaller than the length of the wave. Okay, so other way it doesn't make sense. The whole so the distance. Okay, which approximations are used in deriving these equations? Which is approximate equation? It's clear. For example, what is obvious from the first glance that the distance should be small compared to the wavelength. Okay, so what physical assumptions are used when you write this mathematics?
So those Artyom, can you say about what physical assumptions are used to do this?
The distance between the superconductors
Should be much smaller than the length of the wave.
No, not the wavelength. The coherence length, the size of Cooper wave.
Oh, the size of the wave, okay.
Yes, because
And the second derivative comes from the capacity term.
yes, this is capacity term. Yes. So this I was going to explain. So this is capacity term, and this is ohmic term. This is ohmic part of current, which is equal to V over R.
Okay.
And this is super.
And which coefficients are connected with permeability of the conductor? How is it built in the coefficients? Маркиза проницаемость материала, давайте писать это, ясно.
It is encoded.
Where is it encoded? Which coefficient?
And this parameter can appear in both coefficients.
In both coefficients.
Yes, because it is the dimensionless equation.
Okay.
Oh, so thank you. So, and this equation is called Stewart-McCumber equation. And we will concentrate in this on the special so-called our-damped case, where we can neglect the second derivative term, where epsilon 1 is equal to 0, and epsilon 2 is equal to 1. We can normalize everything to have epsilon 2 is equal to 1. And we take a quasi-periodic case, where the exterior force, f of t, is b plus a quasi-periodic function, plus a times cosine times some frequency times t. And we get a first-order differential equation. And this is the main differential equation we will work with. This is the family of this yields family of dynamical systems on torus, which we will study. So let us pass to the next slide to see the family of dynamical systems. So let us normalize the time. Let us introduce the new time, tau, which is equal omega t. And it appears that after these transformations, including that we also shift the phase difference by pi over 2, this transformation sends graphs of solutions of these equations to trajectories of this dynamical system, which lives on the torus, because the right-hand side is 2 pi periodic in each variable. So we have reduced our problem, our simplified overdamped problem, to a family of dynamical systems on torus. And our main problem is to describe rotation number function of this flow as a function on the space, so on the space of parameters. And moreover, we fix frequency, and we study dependence only on B and A, on the two parameters. B is called abscissa, and A is called orbit. And the rotation number has physical meaning. So if you recall the definition of rotation number, so it is difference of solutions, and solution is a kind of integral, right? It happens that rotation number is up to known constant, is mean voltage for a long time interval up to known constant value, because of this Josephson voltage relation. Because difference of values phi of t minus phi of 0 is, roughly speaking, the integral of voltage. And then we have to divide it by time. And let us recall that phase log area is a level subset of rotation number function in this plane of parameters if it has non-empty interior. And Viktor Matveyevich Buchstaber and Oleg Viktorovich Karpov and Sergei Ivanovich Tertichny, they discovered in 2010 the following remarkable quantization effect, that it appears that the values R, for which it is phase log area, are integer. Phase log areas exist only for integer rotation number values. Let me briefly explain where does it come from. It appears that this equation can be equivalently rewritten as a Riccati equation, as a projectivization of a linear system of equations. And due to this fact, the following holds. So let us realize the sphere, the circle with angular coordinate theta, as a unit circle in the plane, equipped with polar coordinate theta. It appears that the Poincare map, that is time t 2 pi flow map of the torus, which acts on the circle, is Möbius. It extends to a conformal automorphism of the ambient Riemann sphere of this type. And let us now explain the quantization effect. The phase log areas exist only for integer rotation number values. The same effect arises in general families of Möbius circle transformations, which depend on some parameters and which are strictly monotonous in at least one parameter denoted B. Like here, because here it is clear that the bigger is B, the bigger is theta is rotated. So the Poincare map here is monotonous in B. So let us consider the situation of Möbius circle transformation, which are monotonous in B. So for every, if h is identity, then its rotation number is integer, nothing to prove. If h has fixed point, then its rotation number is again integer, nothing to prove. Let us consider that rotation number is non-integer. If rotation number is non-integer, then h is analytically conjugated to a rotation by some obvious map. But it appears that if we take a rotation, just a true rotation, and if we perturb it forward in one and the same direction, then the rotation number changes immediately. It increases immediately. And the same situation happens if h is not a true rotation, but just conjugated to rotation. The same situation is just immediate monotonicity holds. And therefore, there is no, in this situation, there is no chance to keep rotation number the same on an open subset. And this explains that the values, the non-integer values of rotation numbers do not give phase lock areas.
Small a and small b are explicit function of capital A and capital B.
Let me.
The Mobius transform.
They are very, very transcendental function. Very transcendental.
In terms of capital A. And
yes, they are functions, but very, very complicated, very transcendental. So let me speak about generalization of Buchstaber-Karpov-Tretishna rotation number quantization effect. Consider a general family of Wilson groups. Here, F and G are to pi periodic in the corresponding variable. So this is again a family which depends on two parameters, P and A. And let us consider the special case where F is like before. Before F was just cosine, but if we can replace cosine by a linear combination of cosine and sine, the rotation number quantization effect remains the same. Now let us consider slightly different situation, slightly more general, where F contains only one harmonic, cosine m theta plus sine m theta plus some constant. And then it happens that the phase lock areas may exist only for those rotation numbers, which are rational numbers of type k over m, where k is integer. So this proof is basically the same. We can reduce to the case when m is equal to 1 by passing to covering. So,
Can you please explain the name? What is BT?
Sorry?
BKT, what is generalization of
Buchstaber-Karpov-Tretishny rotation number quantization effect. Quantization effect states that in our family, the phase lock areas exist only for integer values of the rotation number. So this effect is called, I called it Buchstaber-Karpov-Tretishny rotation number quantization effect because it was discovered by them. And this is generalization for this slightly more general situation, when F consists of just one trivial harmonic. And I suggest the following conjecture, that if F is not of this type, that is, if F contains at least two harmonics, because with M and N different numbers, then whatever G you take here, phase lock areas will exist for all the rational rotation numbers, like in the Arnold-Tong picture. And this is open conjecture, and there are only partial results. So our theorem with Leonid Rybnikov states that this is true when f of theta is analytic, and when you take a generic g of t, given an analytic f with at least two harmonics, we can adjust g in such a way that here the phase lock areas exist for all the rational rotation numbers. Two physicists, Zaryov and Fominov, observed that if you take a special f with two harmonics, with one and second harmonic, and take g to be cosine, then the same is true. Phase lock areas exist for all the rational rotation numbers, but this is not a mathematical paper. This is an explanation of physical level of rigor. So the told me that there is an open mathematical problem to prove the observation mathematically. So similar systems on torus, as we have seen in the Josephson situation, arise in other domains of physics. For example, in the paper by Bijayev, Borisov, and Mamayev, it was noticed that the big family of dynamical systems on torus, in which rotation number quantization effects holds, was introduced by Hess, famous mechanicist, in 1890. And it appears that in classical mechanics, such systems were studied in problems on rigid body movements with fixed point in works by Hess, Nekrasov, Lyapunov, Glutsyuk, Rukovsky, and others. And many works concern this family, our family of dynamical systems, or its subfamilies. For example, its subfamilies occurred in the work by Ilyashenko and Heimer, where it was studied from the slow-fast system point of view, the canard limit cycles, etc. In a paper by Foote, Levy, and Tabachnikov, it was noticed that this family arises in particular in planimeters and in bicycle dynamics. Now let us pass to our family. Let me recall that we deal with this family, and we would like to understand its phase log areas in the parametry plane of parameters B and A. Before going to detailed description of phase log areas, let me provide some very basic picture.
Question: if I understand it right, both coefficients A and B depends on the frequency. Okay, so when we change frequency, what will happen with the picture?
Frequency, you mean external
Omega,
frequency of current?
Omega.
Omega is external frequency of current.
External frequency.
And it doesn't appear in the equation.
Okay.
That's our
coefficients. I'm sure it's
We can discuss it further.
That's our equation, and frequency is here in the denominator.
Frequency should be
Yes.
coefficients, of course.
Yes, and of course, yes.
Yeah, of course.
Of course, the rotation number function, it will change when we change the frequency parameter. Of course, it will change. And I will show some basic picture. Let us present the picture of phase log areas for omega for frequency being equal to 1. So in white, the flow of the phase log areas are marked. In gray, it's the complement. So in the center, this is phase log area number 0. Here, the rotation number is equal to 0. Here, the rotation number is equal to 1. Here, the rotation number is equal to 2. Here, minus 1, minus 2, etc. The picture will be symmetric. So each individual phase log area is symmetric with respect to the horizontal axis. And the phase log area number n and the phase log area number minus n, they are symmetric with respect to the vertical axis, to the a-axis. And let me, the closed curves here are some effects or secondary effects of numerical simulations. They represent those parameter values for which the multiplier of the Möbius transformation Poincare map at fixed point remains the same.
Yes, to do understand right, that the confined domains, this is integer rotation numbers.
Yes,
domains.
yes, in the white domains.
Different
Yes,
integer
rotation number. Yes,
domains.
yes. Here the rotation number is 0. Here it is 1. Here it is 2, etc. And let me say some words about geometry of phase log areas. It appears that each phase log area is an infinite garland of domains going approximately up to infinity. And each two neighbor domains are separated by one point called constriction. So there are two types of separation points. Those separation points which lie on the abscissa axis, they exist for non-zero rotation number values, and they are called growth points. And their abscisses are well known. This is formula for abscissa. And the other separation points which do not lie on the abscissa axis, they are called constrictions. По-русски перемычки. And now let me represent other value of omega 1/2. And this is another picture, but of similar spirit. And in each phase log areas, there is infinite number of constrictions. So let me now state literally several properties of phase log areas. The boundary of each phase log area consists of two analytic curves, which are graphs of functions, B as a function of A. Each phase log area is infinite garland. I have already told about it, separated by intersection points of these boundary components. And this phenomena, that it's in infinite garland, was observed by physicists Shapiro, Janus, Holly, Likharev, and confirmed numerically by Buchstaber, Karpov, and Tertishny. And this phenomenon, that it is indeed an infinite garland, it was proved by mathematically by Alexei Klimenko, who works here, and Olga Ramoskevich, now Olga Paris Ramoskevich, who works in Lyon now. They proved basically asymptotics of the boundary curves, namely the functions whose graphs are boundary curves have basically asymptotic at infinity. That's it. And now let us state one of the results which I would like to tell about. That's it. So now let us consider the case when omega is equal to 1.3. The interiors of the phase log areas take bigger and bigger space, and the remainder remains very tiny. And there is an important problem. Study the asymptotics of the phase log area form as omega tends to 0. Conjecturally, the limit would be something like chess table turned by 45 degrees. But it is not known whether the limit separation curves that they do exist and whether they will be a straight line or some other curves. This is a completely open question.
You consider that your B is dimensionless, so your L is has the dimensional time. This is time. It's not balance, it's time. L. B is dimensionless, and omega 1 over time.
So this is this picture was obtained by Sergei Ivanovich Tertishny in numerical experiences, and it was his problem which have written these comments. So B is over here. This is 1. This is a point with abscissa 1, 1, 0, half, etc. This is these are values of the coordinate A. Artyom, can you explain these comments, please? The dimensional bias, dimensionally less bias.
Is the right-hand side term, which contains B and A, it plays the role of external graph.
Dimensionless is 1 over time. So L has dimension time. Yes, if you want to have dimension length, you multiply by the speed by the velocity of line. Yes, then you
There is no velocity of light. It's purely mystic.
So it's just strange notation. Substance in time denoted by L. That's all. Yeah. This is very strange notation. That some
For instance, A and B.
L is time. Okay.
A and B.
A and B dimensionless.
No.
Well, the equation is cosine. No, it's dimensionless. Is the equation.
But the left-hand side is definite over dt.
Okay. So does L have dimension? L too small. Does have dimension? Does have.
It is dimensionless.
Dimensionless.
Small is dimensionless.
Okay, dimensionless. Okay.
So one important results which I would like to tell about is constriction alignment. So as you can see here, all the constrictions in each phase log areas, all the separation points which do not lie on the abscissa axis, they lie on the same vertical line. And this is our theorem. For every frequency omega, for every integer number r, okay. Okay, maybe there are some questions.
that is passing the.
Okay. So the theory was the following: that each phase log area, all the constrictions lie in the same vertical line, with abscissa being equal to the rotation number times the frequency times omega. And surprisingly, there are physics books written in the 1970s, for example, a book of Lichreif and others, which presents these pictures, but nothing is said about constrictional alignment. Nothing is said. So, but the pictures are there, and in the pictures, one could have seen that the constrictions are on the same line. This was stated as conjecture in our joint paper with Dmitry Filimonov, Viktor Kleptin, and Ilya Shurov. We have made a certain progress towards this conjecture. And after several years after, it was finally proved in our joint work with Yulia Bibila. And so proof uses different kind of mathematics. So first of all, it uses equivalent description of our model and as a system of as a family of linear systems of differential equations on the Riemann sphere. Let us rewrite our dynamical system family on torus like this, like line field on the torus with coordinates theta and tau. Let us introduce rescaled abscissa L and rescaled coordinate S, and let us write down our equation in the new parameters. And as was observed by Buchstaber, Karpov, and Verschlichny, when we make further a parameter change, when we introduce complex parameter z, which is exponent of it tau, and phi capital, which is exponent of I theta, then this variable change transforms our equation. Sorry for this numeration typo. It transforms our equation to Riccati equation of this type. Riccati equation of on phi as a function of z. And Riccati means that its right-hand side is quadratic in phi. And once one has this means immediately that phi is this equation is projectivization of some linear system. Namely, in our case, phi is a solution of Riccati equation, if and only if it can be represented as a ratio of components of a vector solution of a linear system with this matrix y. This vector function with components y1 and y2 is a solution of the equation y prime is equal to this huge matrix times y. Here R is non-diagonal matrix. Is a matrix with non-trivial off-diagonal elements. And Buchstaber and Tertichny observed that this linear system is equivalent to the special doubly confluent Höyden equation from well-known Höyden class of linear second-order linear equation. The function u of z, which is some exponential function, is the second component. Namely, this function e satisfies this scalar second-order differential equation, which is called double confluent Höyden equation, if and only if one can complete y2 by first component y1 in such a way that this vector function satisfies this linear system.
Can you please comment the following?
Sorry? Yes.
The expression for function e of z is the only one choice to make the function y2 the solution of linear system. Yes.
You can.
It is an if and only if statement.
Yes, if and only so. So the statement is the following: consider these two functions here and y2. Here satisfies this equation if and only if y2 can be completed by some y1 in such a way that the vector function thus obtained satisfies this linear system. It's if and only if. So, and now let us discuss how how do the linear systems help in our situation to study Poincare map and rotation number? So our linear system, let us turn back. That's our linear system. It has two similar points on the Riemann sphere: 0, which is a second order pole, and infinity, which is also a second order pole in the local chart. Second order, also called in analytic theory of differential equations, Poincare rank 1 singularity, irregular singularity of Poincare rank 1. Now let us consider the monodromy operator. Namely, let us take a non-zero, not singular point in that time Riemann sphere, say Z0 equal to 1. And the space of initial conditions of linear system and this Z0 is naturally isomorphic to the space of germs of solutions of the linear system at the same point. It is C2. And when we take an initial condition, initial vector for the solution at the given point Z0, and when we extend the solution along a path which goes around the origin and returns back, this yields monodromy operator, which acts on the germs of solution. It sends the germs of solution before extension to the germs of solution after extension, and it acts on C2. It is a linear operator from C2 to itself. And the projectivized monodromy acts on the projectivized space C2 on the space CP1, or in other terms, on the Riemann sphere with coordinate phi. It is exactly the monodromy transformation of the Riccati equation for the monodromy around the origin. And it is a Möbius transformation because this yields a family of globally holomorphic self-maps of Riemann sphere, and it is clearly Möbius. And in our situation, the unit circle, phi, modulus of phi is equal to 1, is invariant under the projectivized monodromy because the projectivized monodromy can go along the unit circle on the timeline. And when you go along the unit circle in the space, Riemann sphere, this unit circle remains invariant because our complex system was obtained as extension of real system. And a real system means that we are on the torus, which is product of two unit circles, and this means that this circle is invariant when we move in time along the unit circle. And therefore, it is invariant under the Poincare map. And the Poincare map is nothing else but the restriction to this unit circle of the monodromy of Riccati equation, of the projectivized monodromy. We have the following trivial observation that the Poincare map is identity if and only if the monodromy has trivial projectivization. And this holds if and only if the monodromy is just nothing else but identity up to a scalar factor. And we know that the constrictions are characterized by the properties that the monodromy, that the Poincare map is identity. It is topological observation that holds that a point is constriction if and only if its ordinate is non-zero and the Poincare map is identity. Because if it were not identity, easy topological argument would imply that it's not constriction. So now we would like to characterize constrictions and to show that they are aligned. Let us sketch this proof. So first step is the following, that we proof show that at each constriction, the rescaled abscissa b over omega is integer. This means that the b is equal to omega times some integer number. Not necessarily a true rotation number, but some integer number. And this was the first step. Let me explain this first step. Let me recall that our point is constriction if and only if the abscissa or equivalent layers is non-zero and the Poincare map is identity. Or in other terms, S is non-zero and the monodromy of the corresponding linear system is projectively trivial. It is identity up to scalar factor. Now I will use analytic theory of linear differential equations developed first by Birkhoff in the beginning of 20th century, and then developed by German school by Jurkat, Lutz, Berimlov, Balzer in the late 70s.
Excuse me. Sorry, just
Yes.
could you repeat again? What means the constriction?
Constriction is a point, a separation point of. Let me
Okay, so the separation point between the areas, right?
between components of areas.
Okay, yeah.
Yes, these are constrictions, and those separation points
Okay.
which do not lie on the abscissa axis. Yes, and they are characterized by a property that the Poincare map is identity.
Mhm.
And also here the Poincare map is identity as well. But here we require that the abscissa be non-zero, because if the ordinate be non-zero, because if the ordinate is zero, this is not irregular. Zero is not irregular singular point anymore. It is a Fuchsian singular point of very different nature. So that's it. So now we would like to, so we can forget about constrictions, and our goal is to describe those points, those parameter values for which this linear system has projectively trivial monodromy. We can forget everything else. And there is analytic theory of differential equations, linear differential equations on the Riemann sphere, developed by Birkhoff, and then strongly developed by German mathematicians Urquhart, Imhoff-Balzer, and American mathematician Lutz together. And their theory implies that inappropriate canonical basis of solution, of local solutions, the matrix of the monodromy operator is a product of three matrices. One is diagonal, like this, where L is the renormalized abscissa. Lower triangular, unipotent lower triangular matrix and unipotent upper triangular matrix. This canonical solution basis is defined in some sector, nicely defined, and it's called Stokes canonical solution basis. And that for those who knows the theory, the triangular matrices are inverses to the Stokes matrices as the singular poles. I will explain what a Stokes matrix is just in a moment. And now let us require that this matrix, this product, be proportional to identity. Let us write down a linear algebra, basic linear algebra equation, and it appears that this relation is equivalent to the condition that the triangular elements, the triangular elements vanish, and the diagonal matrix is nothing else but identity.
Sorry, I didn't understand why M writes in this.
It is very tricky. It is very tricky issue. It is a whole theory.
So for this is for N monodromy.
No. No, this holds under the condition that the origin we have second order pole. It is a very general statement in the case when we have second order pole here. And here, this parameter, the coefficient here is related to the coefficient here, to the residue matrix. So this term is related to the residue matrix. And these are some triangular matrices, which are called Stokes matrices. It's a very general theory, but it will be presented in details in the next slide.
Okay, so it's like the monodromy map, the linear system where the term with z square is diagonal, and then there is the 1 over z.
Yes, yes, but if the order is higher, there will be a product of big enough of Stokes matrices. There will be, if the pole is of order 3, there will be 2 triangular matrices long here. And now let us imagine that such matrix is identity up to scalar part. Then this holds even if the triangular elements are zero, just by straightforward matrix multiplication. And this diagonal element is 1. Yes, and by the way, this holds even if this is equal to 1, even if L is integer. And therefore, we observe that the assumption that M is projectively trivial implies that L is integer. Just by this very non-trivial theorem, but very deep theorem, and elementary linear algebra. So, now, and by the way, this implies that not only, in this case, monodromy is not only projectively trivial, but it is truly trivial, because these matrices cancel out. They don't exist. Now let me just say some words about Stokes phenomena theory. So in our situation, let me recall which system do we work. So we can forget everything else. The main point that here we have a matrix with different eigenvalues here. And here we have just arbitrary matrix. And here we have anything else, which depends homeopathically on them. We analyze everything. This is a germ of linear system at the origin, a singular point. The theory applies in this very general situation. That's it. The theory states that in appropriate sec, we can cover, in our case of second order pole, we can cover C star, the Riemann sphere punctured at the origin and the infinity by two sectors, in such a way that in each sector there exists a unique holomorphic matrix function H plus or minus Z, which is not only analytic in the sector, but it is continuous in its closure. You see, it extends continuously to zero by as identity. This satisfies the following statement: that the variable change defined by this matrix transforms the initial linear system with arbitrary matrices to a diagonal system of this type, in our case, diagonal matrix, which is called the formal normal form. And this diagonal matrix contains only polar part. It contains no holomorphic terms. This is called formal normal form. And let us take a fundamental matrix solution, diagonal fundamental matrix solution of the formal normal form. It takes this type. And let us return back to the initial system. This is transformation from the initial system to the formal normal form. Sorry, here I should have written y tilde. Here is the type of y tilde here. And passing back to the initial system, we get a canonical fundamental matrix solution of the initial system in the same sectors, which are just product of the fundamental matrix solution of the formal normal form times the transition matrices, H plus minus. This, the columns of this matrix satisfies the initial system. And let us fix some analytic branch of the fundamental matrix, diagonal fundamental matrix on S plus, and just arbitrary coefficients here and there, which are called norm. And let us extend analytically the initial branch of the diagonal fundamental matrix from S plus to S minus, counterclockwise extension. And let us write down the canonical fundamental matrix solution of the initial system thus obtained. So let me recall that system 6 is this one. The W's are fundamental matrix solutions of the system. Now, it appears that on each intersection components of the sector, which are denoted sigma 0 and sigma 1, we have the following relation. We have two fundamental solution matrices of the initial system 6, which are related by some transition matrix C0. And on the right, we have similar relation up to rescaling of W plus by some diagonal matrix, which is monodromy matrix. This is monodromy matrix of the formal normal form. This defines us two matrices, C0 and C1, which are called Stokes matrices of our initial system, which was written on the previous slide. We have defined our Stokes matrices, and now let us return back. Let us return back here. These triangular matrices are inverses to C0 and C1. This is inverse to C1, and this is inverse to C0. And that's it. And this is indeed remarkable formula for the monodromy of transcendental linear systems in terms of its invariants, which are called Stokes matrices, and in terms of the formal normal form. That's it. Now, that's all about Stokes phenomena. And I would like to say that in general, calculation of Stokes matrices is a very, very non-trivial, very, very transcendental problem. This system, so for the formal normal form is found immediately, just by finding jet level, just immediately. But finding Stokes matrices is a whole issue. If you understand Stokes matrices, you understand completely linear system. So now, so what we have done up to now, we have proved that at each constriction, the ratio B over omega, that is this L, is integer number. And now we have to prove that it is indeed a rotation number. It took me several years more. And a constriction will be called correct if this L coincides with rho, with rotation number. Conjecturally, so a posteriori we know that all the constrictions is correct, but when we were proving this, we did not know this, and so we called a constriction host if L is different from rho. And our goal is to prove that the ghost constriction don't exist. To this end, we pass to a new parameter space. We fix L, we fix our integer number L, which is B over omega, and we can introduce two new parameters: eta, which is omega minus 1, and S, which is A over omega. And we place ourselves in the space of these two parameters. And we mark those parameters, eta and S, for which the corresponding triple of points, L, eta minus 1, S, eta minus 1, eta minus 1, which is B, A, and omega, is a constriction. Sorry. So we mark all the constrictions correspond which are situated on the axis B over omega equals to given L. We place all of them to this plane.
All possible rotation numbers appear in the picture. Couldn't they repeat themselves, or they appear only once? I mean, in your figure, the rotation number appears only in one confined region, or it can repeat itself.
No, each connected white stuff is a phase log area, just one rotation number.
Just one. They never repeat itself. Yeah.
No.
All possible numbers.
No. They are ordered horizontally by rotation number. So for each rotation number, there is only one component. Yes. Yes. Now the next step is to prove. Our goal is to prove that the rotation number coincides with this L. To this end, we consider this constriction subset in the two-parameter space. Eta and S, for which the corresponding point is constriction with abscissa omega L. Step 2 is the following theory: that this subset in the positive quadrant is an analytic submanifold. Submanifold means that it is not only local submanifold, but it is closed. It is a closed subset which is locally submanifold. And each component is homeomorphic to in interval. And it is shown that omega takes arbitrary small numbers being restricted to each component. In other words, that eta is an unbounded function on each component. Another part of step 2 is that if a component of constriction submanifold number L contains at least one correct constriction, with L is being equal to rho, then all its constrictions are correct. But this is completely obvious, because rotation number is a continuous function, and therefore, if we know that it is integer and continuous on a component, then it is constant. And the proof of this statement, especially the proof of submanifold property, uses isomandromic deformations, holomorphic vector bundles, as used Bali-Bruch, and Klemenko-Rabutovskevich basic asymptotic of the boundary. Third step is the following: fix a given L Then it is proved, the theorem states that for all the frequencies small enough, the corresponding constrictions which lie here, they are correct. And this theorem is proved by real dynamics methods, by slow fast family theory. And imagine now we have component, arbitrary component of constrictions as a manifold. Well, we know that on this component, omega takes arbitrarily small numbers, in particularly so small, for which we guarantee that the constriction is correct. This implies that each component contains at least one correct constriction. But by the third statement of step 2, all its constrictions are correct. And this works for all components because it is shown that on each component, omega is unbounded from below.
But why, I have a very naive question, why I cannot count s equals 0?
Sorry?
Why I cannot count s equals 0 as a correct constriction?
Because the remarkable monodromy relation fails. But on the other hand, when s is equal to 0, then the equation can be explicitly integrated.
Yeah.
You know, so yes.
Step 2.
Yes.
I cannot say that.
Yes.
It would be trivial, which is not,
Yes.
but I cannot say that s equals 0 in some sense is correct because I
Yes.
can just compute it and then all are correct. No? Why this naive statement fails? It's obviously fails because it's not.
Yes, yeah. Why we cannot approach the eta line, right? Yeah, yes, because actually there is some next slide. Yes, that's the slide about it. Is it?
The question. If I got it right, the frequency, both coefficients A and B depend on frequency, and they become very singular for small omega, right? So is it what happens is the limit if you take formally the limit omega to 0, you will have some very simple dynamical system. Could you explain what will happen in this limit? Formally, without proof, of course, but
What happens when omega tends to 0?
yeah.
It's
very singular coefficients.
It is a very tricky question because our system becomes slow fast family of systems. Slow fast, and the behavior is very tricky, and that's the problem I'm studying right now. Yes. Actually, but on the other hand, when the omega tends to infinity, the system converges to a very simple diagonal system. So the whole non-triviality is when omega tends to 0. But on the other hand, slow fast methods allow to prove that constrictions with small omega are correct. It's another part of story. So Maura, was your question about this somehow?
Yeah, okay, I think it's just a naive question.
Yes, because actually, suppose we have proved that our constriction subset is submanifold, is true analytic submanifold. So manifold means that it goes either to infinity, it doesn't oscillate, it goes either to infinity, or it lends to some axis because it is infinity in the quadrant. Or it lends to 0, etc. And each case, when it lends somewhere, are crossed out by these arguments.
Okay, thanks.
I think your question, why a constriction component cannot lend to the horizontal axis. That's it. Because there is our joint paper with 4 options, which shows that if we compare L, if we take a constriction and compare L with a rotation number, then L is no greater than the rotation number. L is no greater than the rotation number. And if we have, but on the other hand, the abscissa of growth point is greater than then the rotation number times omega. And using these two statements, we prove that a family of constriction cannot limit to a gross point. Because if it limits somewhere on the horizontal axis, it limits to the gross point. This is impossible by these two inequalities.
Okay,
So it's
yes.
so how much time do I have? Okay. Let me just not show you all the details of proof, but just present some spirit of proof. The spirit of proof is the following. So let us hash the proof of theorem A. Let's say that constriction is submain. We use trivial fact that in a transversal intersection of two submanifolds is again a submanifold. And our goal is to realize the constriction subset as a transversal intersection of two submanifolds lying in three-dimensional space. And namely, we take subfamily of our linear systems with fixed L. And it depends on our two parameters, eta and S, from the constriction submanifold combined manifold. And we extend this linear system family to a bigger three-parameter family of linear systems, again with poles at 0 and infinity, which depend on three parameters, in which the monotomy remains the same, and the Stokes operators this family is foliated by one-dimensional family, which are called isomonodromics. Along each leaf of the foliation, along each one-dimensional family inside, monodromy operators, Stokes and transition matrices between appropriately normalized sectorial solution bases do not change. And in each one-dimensional subfamily, each leaf of isomandroic foliation is governed by polynomial equation. And now we have to define two submanifolds whose intersection is transversal and coincides with constrictions. The first submanifold of nothing less just in our initial family, the hyperplane He equals to 0. So He equals to 0 corresponds to the initial family. And main property is the following, that take this foliation by the isomandroic families. It happens to be transversal to this hyperplane. And the second submanifold is the trivial monodromy subset, the subset of those triples of parameters, for which the monodromy operator of the family system from the extended family is identity. That's it. Now let me just write explicitly the extended family. There are several ways to do this, and one way is I have suggested after I have written the paper with Bibila, is to extend a family of dynamical systems by adding extra term, cosine theta minus tau. And this extended family of dynamical systems happens to be also governed by linear systems, which form a three-dimensional extension of initial family of linear systems. And this is the extended family we are looking for. And the isomandromic line field, actually it is induced by well-known Jimba families of isomandromic differential equations. This is the foliation by isomandromic families is tangent to the foliation given by this differential equation. And they are governed by the equation satisfied by this ratio.
Phi is a function of psi.
Yes, chi is a function of psi. Sorry. I haven't written this. Yes, chi. Yes, that's it. That's it. And if we consider a one-dimensional family satisfied with this differential equation, then this gives a family of laws of the torus, which has the property that the rotation number remains the same, and moreover, the flows given in the line in the same family are analytically conjugated between themselves. So this gives dynamical isomandromic foliation in the space of parameters of the family of dynamical systems, which is very interesting to the study itself. So now let me pass to some new results. To some new results, joined with Artem. So there is, so I have told about to the confluent, double confluent Hoyne equation. This is the general case of general 6-parameter family of Hoyne equations introduced by Carl Hoyne. This is each equation has four Fuchsian singularities, except for the generacies happen when the singularities confluent. And they are important in physics because they are related to studying Schrödinger equations, ion of in different quantum systems, ion of hydrogen molecules, Stark effect for hydrogen atom, etc., etc. Black holes. Artyom may tell much more things about it. Now let me pass all the slides and state something very new. Alexander Gorsky asks the following question. So look, in the Josephson case, we have dynamical systems on torus which are described equivalently by double confluent Hoyne equations. We are two pairs of singularities confluent. What about general Hoyne equations with four different singularities? Can they be realized by some nice dynamical systems on torus? And I have observed that if you introduce such family of dynamical systems on torus, you take an initial Josephson case, you divide it by 1 over minus delta times cosine t, where delta is between 0 and 1, and you add some d. Then it appears that this family of dynamical systems happens to be equivalent to general Hoyne equation with explicitly written singularities. And our joint result with Artyom concerns this family of dynamical systems. So if we erase all the non-triviality coming from general point always, then we know that this system has constrictions, infinitely many constrictions in each phase log area. And in new family, the quantization effect also holds. The rotation, the phase log areas exist only for integer rotation numbers for the same reasons, because the monodromy is Möbius. Again, this can be shown. And our theory with Artyom that if delta is non-zero for every fixed delta and for every fixed omega and d, the phase log areas in the new perturbed family in the same plane with parameters b and a have no constrictions with non-zero or all the constrictions of previously considered Josephson model break down when we perturb delta from 0 to some positive number. That's the picture, numerical pictures obtained by Artyom. And proof looks like Stokes matrices argument in the proof of in the investigation of projective triviality of monodromy in the constriction case we've seen before. Constriction, if it exists, it corresponds to the case when the monodromy along the of linear system along the unit circle is scalar. Monodromy is projectively trivial. But the monodromy is a product of two monodromies around two singular points, 0 and some alpha, which is inside unit disk, because inside unit disk there are two singular points, and they are symmetric to the, in some way, to the other two symmetric, to two singular points which are outside the unit disk. And therefore, the product of these two monodromy matrices should be projectively scalar. This means this implies that they have a common eigenvector, and the ratio of their eigenvalues are equal up to taken inverse. This is these 2 points, and nothing else but just very basic linear algebra. And the eigenvalues of M0 and M alpha, they are calculated as exponential of 2 pi times residue eigenvalues of the linear systems at the singularities. And this implies some conditions on residue eigenvalues. And the miracle is that this condition of residue eigenvalues, which is very explicit, this implies that the ordinate should be 0. This is indeed a miracle, which explains all these pictures. Still, the next slide, and I will finish. On the other hand, when A is equal to 0, when the orbit is 0, and a priori constrictions are possible, and Artyom's picture show that the constriction do exist. And
What is D?
D is that's A, and that's T. And the next theorem saying that if constriction exists, then these constrictions are organized along hyperbolas. To the constrictions in the plane B with parameter B and D, when A is equal to 0, the constrictions are organized along these hyperbolas. And this fact also comes from analyzing the residue eigenvalues as before. That's just from writing down a necessary condition in terms of residue eigenvalues for monodromy being projectively trivial. So that's all. Well, thank you very much.
Did you try to present this stuff to the physical audience, and
Yes.
which points sparked some interest? What was interesting in this stuff for qualified physicists?
Yes, actually, the very first version of our paper with Bibila was read by Sergei Tertichny, a physicist, and he liked very much.
What particular points are new for physicists? Yeah.
So particular, actually, he was a kind of informal referee of because I was going to present a short note in the Russian mathematical surveys, and he wrote a referee report. But actually, from a referee report, I have seen that he liked the approach, the mathematical approach, because actually Tertichny is a special physicist. He does a lot of mathematics.
Right.
But on the other hand, I gave a talk. So I told about it to Artyom and to his teacher Alexander Gorsky.
What about your talk in
Yes,
Landau Institute?
yes, I talked about it in Landau Institute. So there were a lot of questions. I had an impression that it was interesting to physical audience, and one of physicists confirmed that it was interesting. But yes, but when I have shown to them this equation, this family of dynamical systems, and which is related to general Huynh equation, and I asked them, does this system realize somewhere in physics? They were not able to answer. They had no idea about it.
The most interesting question is the rotation number quantization is indeed quantization? So it has quantum mechanical nature or not? And in particular cases, the answer is yes, because the appearance of these phase-locking domains is the analog of Black-Labeling theory.
There are a lot of physical noise about quantization of magnetic monopoles. Is it related somehow or not? A lot of good physicists are talking about quantization of magnetic monopoles.
No,
It's a different topic, no intersection.
when you speak about when you try to consider something like a monopole, you should consider the mapping between spheres. For instance, you write down your equation of motion, then you consider specific configurations, and they have topological charge, and the Riemann number, the rotation number, is all the topological invariant, but it is a very peak invariant. It is not related directly to the instantons or some other topological solutions.
Which problems remain open here?
Okay, so first of all, problems which I work on right now is about asymptotical to phase-local report as omega tends to 0. And there are other open problems I can show. Connectivity conjecture. Well, connectivity conjecture is the following. Consider a phase lock in the upper part of a phase lock area. And let us consider the straight line, the vertical line, which contains all its constriction. Let us take the intersection of the upper part of this phase lock area with this line. The conjecture that it is connected. And this conjecture is related to some algebraic geometry. Because the boundary point of this of the intersections are known to lie to satisfy some algebraic equation. Are known to lie in some algebraic curve. And it is to study this connectivity conjecture, it is important to study the geometry, real algebraic geometry of this algebraic curve. And I can show that the algebraic curve described all the potential in the boundary points. The algebraic curve is this. It is defined, it is given by equation saying that a remarkable three-diagonal matrix has zero determinant. And there is another series of open equations. It concerns three-dimensional phase lock areas in the three-parameter spaces, space B, and omega. There is still something to do to show that each individual phase lock area is a garland of domains separated by constriction curves. It is almost proved, but there is some small issues which remain. But what is important is how to pass from lower component to upper component. The way to pass is conjecture is to take the Poincare map of the dynamical isomandromic foliation. Take a system corresponding to some point in the interior of phase lock area. Let us take the corresponding trajectory of leaf of isomandromic foliation. Imagine that this leaf returns back to the initial family. And a conjecture, it lends the first return point will live on the upper, in the upper component of phase lock area. I have a small progress in proving this near conflictions. But this is somehow related to extendability of solutions of appropriate solutions of Lewis equation, etc. So. This would be kind of self-similarity map between different components.
Can I ask one question?
Yes.
If we start from the general Boyle equation, we can rewrite this equation into the linear system.
Yes.
You know that for specific cases we have a invariant circle and we have dynamics on the circle effectively.
Mm-hmm.
What about if we don't have invariant circle, but we still have some invariant curve, like a parabola, hyperbola, something like that? I mean the following: when we try to classify Möbius transformations, we deal with elliptic transformations, hyperbolic, loxodromic, and parabolic. And it seems that for elliptical case we have invariant circle, of course. But if we consider the Riemann sphere, can we expect that something like invariant circle, in some sense, for general Boyle equation can appear, even if this Boyle equation is not related to your systems?
I think this is a question about the following: which Möbius transformation may fix an ellipse or something like this? May fix yes, it's the question, because if you have a Möbius transformation which fixes a closed curve, a journal curve, this means that its multiplier at fixed points are either real or in line on this curve, or they are modulo x is equal to 1, and therefore the transformation is elliptic. But if it is elliptic, besides an ellipse, it has an invariant circle, right? It has family of invariant circles. And I believe the case, there are not many Möbius transformations which fix an ellipse. Indeed, I don't believe that. I did not think about this, but this sounds to be easy. I believe that they don't.
So if you start from a very general Boyle equation, which doesn't satisfy your criteria to have invariant circles, it's almost surely we don't have any nice dynamics.
I don't, yes, because just let us try to calculate the group of Möbius transformation preserving an ellipse. I think it should be reduced to something trivial like a group of order 2, 4, something like this. I believe so.
Okay.
I have still to think about it, but it sounds like plausible.
Questions?